Good day. In this lecture, we will discuss radioactivity, focusing on nuclear reactions and different types of radioactive decay. By the end of this lecture, you should be able to differentiate nuclear fusion and fission and identify and analyze different types of radioactive decay. Radioactivity was first observed by early scientists studying spontaneous emission from certain elements. This marked the discovery of nuclear reactions, which differ fundamentally from chemical reactions. We have here Antoine Henry Becquerel, which is the first person to discover evidence of radioactivity from nuclear reactions. Well, in nuclear reactions, we deal with subatomic particles such as the alpha particles, the electrons, the positrons, the protons, and the neutrons. Each of these plays a role in nuclear transformations. Radioactivity in this case is the spontaneous emission of particles or radiation from an unstable nucleus. An unstable nuclei, also called your radionuclides, undergo decay to become more stable nuclei. This process always involves a nuclear reaction, not a chemical one. The first type of nuclear reaction is alpha decay. Well, in alpha decay, the nucleus emits an alpha particle, which is essentially a helium nucleus. This means that the mass number decreases by 4 and the atomic number decreases by 2. This is a nuclear reaction where the element changes into a different element. We have here an example of uranium-238 undergoing alpha emission. Under this, it will be transformed into thorium-234 by emitting a helium-4 particle. The next type of radioactive decay is your beta decay, or what we call your electron emission. In beta decay, a neutron is converted into a proton and an electron. The electron is emitted as a particle in this case. For the key changes, the mass number stays the same, but the atomic number increases by 1, which is actually critical because a neutron becomes a proton, altering the identity of the element. For this example, we have your iodine-131 undergoing beta emission, which is being transformed into xenon-131 by emitting your electron particle. The next one is positron emission. In this case, for positron emission, a proton is converted into a neutron and a positron is being emitted. For the key changes, the mass number remains the same, however, the atomic number decreases by 1. This is essentially the opposite of your beta decay. In our example, we have your carbon undergoing positron emission being transformed into boron plus an emission of your positron. Next, we have your electron capture. In this case, an inner electron is absorbed by the nucleus. A proton is converted into a neutron. Again, the mass number remains the same, however, the atomic number decreases by 1. This is another way for unstable nuclei to adjust their proton to neutron ratio. Lastly, we have your gamma emission. And for this one, the nucleus releases excess energy in the form of radiation. In this type of emission, there is no change in mass number, and there is also no change in the atomic number. This is not a transformation of particle, but a release of energy after nuclear reaction. Now, when you are writing nuclear reaction, you must always satisfy two conversion law. First, the total mass number must be conserved. And second, the total atomic number must also be conserved. This is actually similar to balancing chemical equations, But now, we balance nucleons and the charge. When you are solving nuclear reaction problems, always check both sides of the equation. If the mass number or the atomic number does not match, the equation is incorrect. And this is actually the most common source of error in the exams. Now, let's answer the question, why does decay occurs? Radioactivity decay occurs because of unstable nuclei. Protons repel each other, while neutrons help stabilize the nucleus. If the ratio is not optimal, the nucleus undergoes a nuclear reaction to reach stability. The neutron to proton ratio determines the stability. If this ratio is too high or too low, the nucleus adjusts through decay processes such as beta decay or positron emission. Now, there are two types of nuclear reactions. The first one is nuclear fission, and in this case, a large nucleus splits into smaller nuclei. This process releases a large amount of energy and is typically initiated by neutron bombardment. And this type of nuclear reaction is the principle behind nuclear power plants. Next type is your nuclear fusion, and in this case, small nuclei combine to form larger nucleus. This process releases even greater energy than fission, and it powers the sun and the stars. However, it requires extremely high temperatures and pressures.